So last week, we ended with some antiderivative computations. We had some antiderivative rules. Now, for a derivative, we started with a function. We made a new function, which had properties that we studied for about 2.5, 3 weeks. The antiderivative is doing the same essential thing, but in reverse. And there are some parallel rules for computing those antiderivatives. And they were listed on the test. But let's just recall one example we covered. Recall the function f of x equals 5x to the fourth has, well, maybe I should say, well, yeah, I'll say has more than one antiderivative. And we saw, I believe, 3 examples last week. It has more than one antiderivative. What are they? Well, one of them we found was x to the fifth, because the derivative of x to the fifth is 5x to the fourth. But we also recalled that the derivative of any constant is 0. So another possible antiderivative for 5x to the fourth is x to the fifth plus 1, because the derivative of x to the fifth plus 1 is also 5x to the fourth. And that constant can be any constant. Now, it could have been, I forget the constant I used last week. This time I'll write negative pi. The derivative of that third possible capital F of x is also 5x to the fourth. So a natural question arises, how many antiderivatives are there? Well, this can be any constant. So already we know we have an infinite number of antiderivatives because the derivative of any constant is 0. But notice the only difference between these 3 possible choices is contained within that choice of constant. The x's are the same in each choice. And a question could arise, are there any antiderivatives where the x terms look any different than just, in this case, x to the fifth? And the answer is no. And let's call that a theorem. The answer is no, meaning the only other antiderivatives of 5x to the fourth look like this with some constant. So theorem, let's call it general form of the antiderivative. Now, on the exam last week, if you chose any constant, it would have been right. I believe the directions for problem 9 said find an antiderivative, find a function capital F, which satisfies f prime equals lowercase f. And the reason is because there's more than one choice. But as we'll see in this theorem, all other antiderivatives differ in that constant. So a general form of the antiderivative is the one we find plus any constant. That gives you all possible antiderivatives. So let's write that down. Let capital F be an antiderivative of lowercase f. So capital F is an antiderivative of lowercase f, meaning capital F prime equals lowercase f. Then any other antiderivative of lowercase f is of the form capital F plus constant and differ by a constant. And this capital C will be a standard choice of constant. Any other antiderivative of lowercase f is of the form f of x plus c for some constant c. And you can see that recollection over there is consistent with this. We found an antiderivative. Here's one. And any other, well, the other two that we found differed by a constant. Now, the general form of the antiderivative, notice this gives a family of functions. It gives all of these capital F, but they differ by a constant. Now, this constant can be anything. So, in general, the set of antiderivatives, well, it is a set of functions which differ by a constant. How do I want to phrase this? I don't want to phrase it how I was about to. Well, yeah, maybe I'll do that first. So we have this result which says any antiderivative is any other antiderivative is of this form. In particular, any antiderivative is of that form because 0 is also a constant. This language, the general form of the antiderivative, is a little cumbersome. And it also introduces some mild confusion, because sometimes you may just want to talk about one antiderivative, sometimes you may want to talk about all of the antiderivatives. So talking about one antiderivative, you could just say an antiderivative. Talking about all of them, we're going to call it something else. And let's define that here and then do an example. This is a pretty important definition. So at the beginning of the course, I mentioned that calculus 1, is largely divided into 3 categories: limits, derivatives, and integrals. And the first, well, really the second week was about limits. The third, fourth part of this week, meaning the video we did for this week on optimization, is on derivatives. And then the last week will be on integrals. And here we're going to define our first integral. Let f of x be a function. We will talk about 2 different integrals. We'll talk about both of them today. The indefinite integral. So the first, as is consistent with the syllabus schedule, the first integral we'll talk about is something we call the indefinite integral. Second one will be the definite integral. The indefinite integral of f of x. So start with a function, the indefinite integral of that function, and we're going to have some notation for this. More on this notation later today and probably tomorrow. Denoted that is a large, what looks like a stretched out S, an integral sign we call this. Integral of f of x, lowercase dx, that's read with respect to x or dx. More on that notation later today and tomorrow. But right here, the indefinite integral of f of x has that notation. And what is this defined as? I should put a comma after this. The indefinite integral of f of x denoted that gives the most general antiderivative of lowercase f. Maybe I'll just say is the most general antiderivative. Antiderivative is a long word. Is the most general antiderivative of lowercase f. And what does that mean? Well, it's going to be given by the results in that previous theorem. So I'll write that as a further clarification. It's going to look a lot like this theorem, but I'd like it to be contained within that definition. That is, so continuation of this definition, that is integral of f, the indefinite integral of f of x with respect to x equals capital F of x plus constant c, where capital F of x is any anti-derivative of f of x. It's not really that important for this definition. This notation, integral of f of x with respect to x, gives the most general antiderivative. And from that theorem, we know that the most general antiderivative is an antiderivative plus a constant. I should say c is a constant, where f is any antiderivative and c is a constant. So last week, we introduced the antiderivative. Now, the reason for introducing that last week was to get some familiarity with that computation, because that computation is going to be important for a good portion of what we do today and a good portion of what we do tomorrow. And between today and tomorrow, so Wednesday night, it'll be good to practice some of these. And I'll tell you more on which ones of those you can practice later. But let's do an example to illustrate this. This definition has a lot of words. We did some antiderivatives of 5x to the fourth. Let's do two examples. So the integral of 5x to the fourth with respect to x. Well, we had a list of 9 antiderivative rules. We'll add a 10th to that this week, and there's a reason I didn't do it last week. But one of those rules said when you add x to some number, you could apply the opposite of the derivative power rule. So an antiderivative power rule, 4 plus 1 is 5, divide by 5, and add 1 to the exponent. Either way, or just from the remarks earlier, derivative of x to the fifth is 5x to the fourth. Either way you want to get there is okay. But this is incorrect because, well, any questions about, well, this is incorrect. I'll go to any questions in a moment. Why is this incorrect? Well, the indefinite integral doesn't say give me one antiderivative. It says give me all of the antiderivatives, the most general antiderivative. Well, this is only one of them. How do we make it all of them? We add a constant. This is a capital C. Earlier we've been using lowercase c's, or earlier we used lowercase c's. But this is pretty standard to use a capital C in this context. Well, very standard. So right here, this does give all antiderivatives. We found one using our antiderivative rules, and we made it all of the antiderivatives by adding a constant. So if you have an indefinite integral, you need all antiderivatives, meaning you need to add the constant c. Because the indefinite integral, by definition, gives all antiderivatives, gives a family of antiderivatives. Any questions about this computation here? Okay. Let's do one more and then we'll give some indefinite integral rules. My notes are out of order. In order. Let's do one more. Let's do one with trig. Just like with antiderivatives in this first one, we could check our work by taking the derivative of this right side. Derivative here, 5x to the fourth, so 5x to the fourth. How about for cosine? Well, we had in our list of antiderivative rules, the derivative of sine is cosine. Derivative of sine of x is cosine of x. But again, we want all antiderivatives here. So what we can do is give all antiderivatives by throwing a constant on there. Any questions about that? Remembering the constant is important. When I took calculus, I didn't fully grasp why the constant was so important, but in the back of your mind, well, we're going to have two integrals today, and they're both going to be what look like different computations until tomorrow. But the one gives a family of functions, meaning it gives all of these functions. And the other one, well, more on that. But let's we had antiderivative rules last week. Let's give some indefinite integral rules. Now, these are going to look like we're doing the same thing twice, and we, in some sense, are. Usually, I like to do integrals, indefinite integrals, and antiderivatives on the same day. But I decided to put some space between them, and because especially for a 6-week class, the antiderivative computation is important. And because of that, I usually write only one of these lists of rules, but here I'll do it twice because the flow of the class makes that seem more useful. Indefinite integrals. So this will be a list of 10 rules. So there will be one which is not parallel to any of the antiderivative rules. Indefinite integrals. Well, first, there will be 10 of these. That's a k. K with respect to x. K here is a constant. We don't use c. So last week when we did the antiderivative rules, it may have seemed strange that we used k instead of c for the first one. The actual reason is because we don't want a lowercase c and a capital C to be all over the place. That's more confusing than it has to be. So here, integral of k. Well, the antiderivative rule said that the derivative of kx is k, so an antiderivative of k is kx, but the indefinite integral says to take all of them, meaning add a constant c. In these computations, c is so standard in this context that after all of these, you don't have to say where c is a constant. Like I wrote up here. In these computations, I'm not saying where c is a constant. It's it's a couple hundred years standard, so that's fine. But this k, I will specify as a constant. So I'll just say where k. I'd normally write this after that, but I don't have room. Where k is constant. And c is constant, but it's standard. Next, we have the power rule. X to the n with respect to x. 1 over n plus 1. X to the n plus 1. I believe last week when doing antiderivatives, I forgot to specify n can equal 1. Now that was okay last week because it never came up. But notice here if n equals, or sorry, n can equal negative 1. I think I said possible. Notice here n can't equal negative 1 because of that denominator. So here with the antiderivative rules, we have one antiderivative. adding a constant c, a capital C, gives us all of them. And here I'll just specify that n can't equal -1. Now, what happens when n is -1? Well, we didn't cover that last week because I wanted it to be this week. Covering it last week may have been overkill. So what happens when n equals -1? Well, we have a third rule, which is not going to be, so I said we're going to have 10 rules here. This third one will be the one not covered, or the one without an antiderivative rule paralleling it. And you could do it, I just didn't want to get into it last week. When n equals -1, you have x to the -1, which can be written as 1 over x. So here, we need a function whose derivative is 1 over x if we want to do this integral. Fortunately, we know one. The natural log of x, the derivative of the natural log of x, is 1 over x. But remember, we would like this integral to be defined everywhere it can be, meaning everywhere except 0. And is there an integral which hits all possible x values? Well, is there an antiderivative which gives this integral for all possible x values? Meaning, what about negative x's? Log of negative x doesn't exist. Log, remember, looks like this. So it never gets at 0 and never gets on the other side. 0 is not going to matter because it's in the denominator. What about the negatives? Well, it's a little subtle, but there is an antiderivative which works for all x in the domain of 1 over x. And we can find that by taking the absolute value of x. Here's one antiderivative, and this makes it all of them. Now, why does that work? Well, as I mentioned before, it is a little subtle. So this is going to be a list of 10 things. You may want to write this separate from your list if you're writing these. But for board space purposes, I'm going to have to write it here. So it will probably be useful if you keep writing your list of 10. And then deal with this. Actually, I'm going to do that. I'm going to write the list of 10 and then deal with this. Because the other 7 don't really introduce anything new from last week or compared to last week. Next, and then we'll get back to that absolute value. Well, any questions so far? We're going to do some computations with all of these. Well, maybe not all of them, but with most of them in a moment. Next, integral of e to the x. Well, we had that e to the x is an antiderivative of e to the x. Derivative of e to the x is itself. So if we want all of them, plus c. So we have these 4, and the next 6 will be for our trig functions. First, integral of cosine. Why are we starting with that? Well, I'm going to have these parallel our derivative rules. The derivative of sine is cosine. The derivative of sine of x is cosine of x. How about the next one? Well, the derivative of cosine is negative sine. So this right here, what's written, isn't going to work. The derivative of cosine of x is negative sine of x. But if we throw a negative on there, the derivative of negative cosine of x is negative sine of x, which is positive sine of x. And then we have the rules for the other trig functions. We have the rules for the other trig functions. Integral of secant squared of x. The other trig functions, the next one is tangent of x. Why did I write secant squared of x? Well, because tangent of x does not have a convenient antiderivative, but the derivative of tangent of x is secant squared of x. So we can compute the indefinite integral of secant squared of x, because the derivative of that right side is this secant squared of x, this integrand, integrand. What's between the integral sign and the dx? And we have four others. Why doesn't the integral of tangent? Why isn't that a convenient computation? Well, I'll mention that after logarithm. I'll write myself a note with all these things I mentioned. What's our next? We have three more. Well, the derivative of cosecant of x is negative cosecant x cotangent x. So the integral of cosecant x cotangent x is negative cosecant x. And the integral gives all of them, so negative cosecant x plus constant. And then we have our last two, integral of secant x tangent x. The derivative of secant x is secant x. That's incorrect. What is incorrect about that line? Well, it's not a negative sign. What is incorrect about that? Looks okay, sort of. Integral requires a variable of integration, meaning a dx. The derivative of secant x is secant x tangent x. So the integral of secant x tangent x is secant x plus constant c. And last, for this list, integral of cosecant squared, the derivative of cotangent of x is negative cosecant squared. So the derivative of negative cotangent x is negative cosecant squared of x, which is positive cosecant squared of x plus a constant. So we have this list of 10 indefinite integrals, 9 of which parallel our antiderivative rules, the 10th of which could, but I didn't want to get into that absolute value last week because last week we technically didn't need it. So before doing some computations with these and well, discussing some properties of the integral, let's mention two things. One, why does this absolute value work? Well, so I'll say y log absolute value of x. Well, first of all, we would like this integral to be defined everywhere that 1 over x is defined, meaning for positive and negative x. 0 doesn't matter because this isn't defined at 0. But why the absolute value of x? Well, take the derivative of the logarithm of absolute value of x. What do you get? Well, the absolute value is defined piecewise. How is the absolute value defined? Maybe I should write it like this. Okay, I'll finish writing this. I should have defined the absolute value or recalled the definition of the absolute value. So this will fit. This the rest of that piecewise piece will fit on those lines. But what's the how do you take the derivative? Well, derivative of that. Well, you're going to need the definition of the absolute value. So first of all, this is going to be defined differently on the positive and negative sides of 0. Here, what happens at 0 doesn't matter because it's not defined at 0. But what's the derivative on the right of 0? Well, to find that derivative, you need to first evaluate the absolute value. For this piecewise function, the first piece will be for the positive side. On the positive side, absolute value of x is x, so log of absolute value of x is log x, and the derivative of that is 1 over x. And that's for x positive. What about for x negative? Well, the absolute value of x negative evaluates to negative x from that bottom line over there. The absolute value of x for x negative is negative x. So for x negative, we need to take this derivative. What do we get here? Well, derivative of logarithm. This is not just an x. It's a negative x. So we need the chain rule. We get 1 over negative x times the derivative of negative x, which is negative 1. The negatives cancel. I don't have an eraser. So by the chain rule for that bottom piece, a second negative 1 shows up. Negative 1 divided by 1 is just positive 1. And this down here is for x negative. This up here is for x positive. But in either case, the derivative of this right-hand side is 1 over x. So right here, we found, well, we showed that an antiderivative of 1 over x can be defined on both sides of 0, meaning can be defined for all x in the domain of 1 over x. Any questions about this? And you may be wondering in the back of your mind, will I ask you why absolute value of x? No, but it is something within week 3 chain rules grasp. So it is definitely worth observing. Second thing about that list that I would mention is there was no integral of tangent of x. So another question that you could ask is why no integral of tangent x with respect to x in that's an A, list? Well, why is there none? Why is there not one? Well, you would need a calculus 2 result to find that integral. You would need a chain rule corresponding to integrals. And that's not a Calc 1 subject. What is the integral of tangent of x? Well, one of our worksheet examples, it actually did show up, and I didn't mention that intentionally. In, I don't remember, it was week 4, maybe 3. Yeah, it was week 4, maybe it wasn't a worksheet example. One of the logarithmic differentiation problems resulted in our having a term. I believe we did the derivative in logarithmic differentiation. So last Wednesday, we did the derivative of cosine x to the x. And we had as the answer cosine of x to the x times log cosine x minus x tangent x. So if you take Calc 2, you will see how to do this computation, but earlier in the semester, we did see part of it with that log cosine x term. There's another part, which you'll see more in Calc 2. But Now, for this class, we don't have a result we would need for that, so we will not cover an integral of tangent of x. Any questions about that? I forget if that was a worksheet problem, a homework problem, or a lecture problem. I should be able to remember that. But, so any questions about this before we do some computations? Well, let's do one more thing before computations. These computations are pretty important. They're very important to practice. But before we get there, we need to discuss two properties. Properties of the indefinite could be called a theorem, we'll just call it properties. We had, so indefinite integrals evaluate two families of antiderivatives. We had derivative rules. Last week, we informally said that antiderivatives can also be done piece by piece, just like regular derivatives. But let's formalize that piece by piece property for these. I need words first. Let's formalize that for these integrals. Let capital F, do I need X's all over the place? Yeah, I'm going to use the X's. Let capital F and capital G be antiderivatives. Let's save some letters. Be antiderivatives of lowercase f and lowercase g. Respectively. I always thought that respectively was redundant in that case because order should be assumed. But I'll write it here. Let f and g be antiderivatives of f and g, and let k be a constant. Then, well, I'll just write them as properties. Let's do 1 and 2. Now let's do a and b. Then the integral of lowercase f plus or minus lowercase g. One of the conveniences of derivative computations was that when you had something plus something else, you could do them piece by piece. That applies to antiderivatives as well, and because of that, it applies to indefinite integrals. So the integral of, or the derivative of capital F is lowercase f, the derivative of capital G is lowercase g. But we need all antiderivatives, so we have our constant. That's a plus c, that they kind of ran into each other. Plus c. So we can do these one at a time. Now you may, especially in the next computations, you may think, well, we have two different things. Should there be two constants? Well, you can smash the two constants together as one constant. 5 plus 7 is still a constant. There's our first property. Our second property, one of the other conveniences of derivative computations, was that if you had a constant multiplied by your function of x, then you could deal with the constant first, or you could pull the constant out and then deal with the x's. And that applies as well. Now, getting constants out of the way was useful for derivatives. It is exceedingly more useful for integrals, especially as you get into Calc 2 and Calc 3 integrals. Getting the constants out of the way makes certain things much more clear. So we can take this constant, pull it outside of the integral, and then evaluate. We get k times capital F. We need all antiderivatives, so plus the constant c. So we have these two properties. Any questions about these two properties? if you have questions about these two properties, they'll probably be clarified in using some of these examples, doing some of these examples. So any questions before we get into these examples? Okay, let's do 3 examples. Evaluate each indefinite interval. Evaluate each indefinite interval. We'll do 3 of them. I kind of want to do these on the first board. I'm going to move this to the first board. Evaluate each indefinite interval are the directions for this example. I'm going to write them on the first board so I can just go straight across the board. And to do these examples, we're going to use these 2 properties I erased and our chart of antiderivatives, or our chart of indefinite intervals. First, part A. Integral 4x cubed plus e to the x plus 5x negative 4 with respect to x. Let's write the other 2. Part B, is that B showing up on camera? So A and B are slightly off screen. They're A and B in parentheses. The math is still on screen. X squared plus 2 plus root x over x with respect to x. Part C, which I believe is on camera. Yes. Integral of tangent x times cosine x with respect to x. Okay, so let's do these 3. Let's do them one at a time. Let's erase those directions because part A's computation is going to run into them. Evaluate each indefinite integral. Well, we have 10 indefinite intervals. We have 2 properties. So let's use them. First, for part A, we have 3 things added together. 4x cubed, e dx, 5x to the negative 4th. So we can do these one piece at a time. For part A, I will show the use of those properties. I'll show the application of those properties. For the others, I might jump over a couple steps. But by property A, we could do this one piece at a time. First is 4x cubed. Now let's throw a negative. Sorry, I should have put a negative. I want the negative on, not the last term. Sorry about that. I've never liked having to change a positive into negative because I always wrote in pen. So sorry, that second one's a negative. But we have 3 things added together. One's added with a negative sign. We can do them one piece at a time. Notice we split with a negative there. We can't split with a negative there. We can do them one piece at a time. Well, what about this first piece? Well, there's a 4 in the way. Let's get that 4 out of the way. The next piece, I'm gonna leave alone for now. The last piece, there's a 5 in the way. So that first equal sign, we used property A from that theorem. The second equal sign, we used property B from that theorem. Pulled the constant out. You could have made this a plus sign, put the negative in here, and then pulled out the negative using property B to get there. I don't know, I'd rather do that in one step, I think. just split it with a negative. But how can we do these integrals now? Well, first, we have x to a number. So by rule 2 from our list of indefinite integrals, we have our power rule. 3 plus 1 is 4. So we get 1/4 x to the 4th. Let n equal 3 in that power rule. You get 1/4 x to the 4th. And more on the constant in a moment. Next, the derivative of e to the x is itself. So an antiderivative of e to the x is itself. And last, we have another power rule, this time with exponent -4. -4 plus 1, -4 plus 1 is -3. X to the -4 plus 1, x to the -3. Now, technically, a constant arises from each integral. So technically, you could have a plus a constant, plus a constant, plus a constant. But you can, and we will, and it's standard, to assume all of those constants smashed together as one constant. Instead of having 3 c's all over the place, let's just put 1 c there. Now, 1 c is much less writing than 3 c's, especially because for the other 2 c's you have positive signs. So we're really saving 4 terms from showing up. Now, right here, there is some fraction reducing that can be done. 4 times a 4th is 1. 5 divided by -3, -5/3. You should combine fractions. It's a good habit to get into combining fractions like that. Now, we can check our work. Well, before checking our work, in this example, we did illustrate theorem property A, theorem property B, and a couple of our indefinite integral rules. Just like with derivative computations, we would like these computations to also be consolidated into 1 or 2 steps. And we'll do that for parts B and C. But before doing that, notice that, as mentioned before, we can check our work by taking the derivative over here. And the checking our work observation, let's check our work, then I'll make the observation. Take the derivative of this rectangled quantity. What do you get? 4x cubed minus e to the x plus 5, because the -3's cancel, x to the -3 minus 1, x to the -4. So 4x cubed, negative e to the x, positive 5x to the -4th, plus 0. So we can check our work here. The checking our work process, pretty much every one of these I've done for the last 10, 11 years, however many years I've been doing these. Let's see, senior year of high school. I forget what year that was. 10? Pretty much, so yeah, 11 years. Pretty much every one of these I've ever done. I've gotten an answer and then just checked quickly by taking a derivative. And that's also a pretty good habit to get into. Another useful habit, I find it useful for derivative taking purposes. The way I wrote the rule for the power rule, and not equal to -1. I wrote it with this right-hand term, with this fraction out front. It's common to write this as just one fraction. I tend to prefer this one, even though it is more writing, because I think it makes the checking your work step a little easier. And I think it makes things pop out more. But of course, you can do it directly. So any questions about that first one? Okay, let's do the second one. First, there is no quotient rule for taking antiderivatives. Meaning, let's write this in red, because red usually means danger, I think, in some contexts. What if you thought, well, integral, we can just go piece by piece. And you said 1/3 x cubed plus 2x plus, what is that, 3/2? No, 2/3 x to the 3/2 all over half x squared, and it's c. So what if you did a few power rules like that? Well, that would work if the integral could break into a quotient. But integrals can't break into a quotient. Meaning, we can't do integral, integral, integral over integral. That doesn't work. We have those 10 rules. Put larger scribbles through this. We have those 10 rules. That's pretty much all we have. So what can we do with this? Well, we can get a larger piece of chalk. I'm running out of larger pieces of chalk. Well, I guess I'll have to deal with it. What can we do with this? Well, we can break the fraction apart. Let's put a large X through this equal sign. I didn't scribble that on. What can we do? We can break the fraction apart. What is that? Well, we can split the fraction into 3 pieces by dividing by that x. X squared divided by x is x. 2 divided by x is 2 divided by x. Root x divided by x is x to the negative 1/2. Now, x to the half divided by x to the first, you're left with x to the half in the bottom. And because we're going to eventually need a power rule, I'm going to just write that as x to the negative 1/2. Any questions about splitting that fraction into those 3 pieces? Okay, now we can do this piece by piece. Because integrals can break sums apart, they can break differences apart, but they can't break quotients apart. They can't get into products either. There's no product rule for antiderivative computations. But what can we do here? Well, here we have an exponent of 1. 1 plus 1 is 2, use the power rule. What can we do for that middle piece? Well, we have x to the negative first. The power rule doesn't apply to x to the negative first. But we have that convenient third rule in our list of integrals, which tells us that the derivative of the logarithm of absolute value of x is always 1 over x on its domain. So if we throw a 2 in front, we can just throw a 2 in front here. This 2 from part B of our properties. The 2 carries along, you're left with a 1 over x. Apply rule 3 from the indefinite integrals. Any questions about that second piece? Okay, how about the last piece? Two x to the half. Where did that come from? Well, if 2x to the half is the correct third piece, then if we add a constant, that's a lot of 2's. Then if we add a constant c, we can check our work and then see if this is right. Well, is this right? Derivative here, 2x times a half, okay. Derivative of the next piece, 2 over x, okay. Derivative of this piece, 2 times a half, that cancels, x to the negative half. Derivative of this piece is 0. So this does look right. But where did that come from? Well, it came from power rule. It said in the power rule that n can't equal -1. N can equal -1/2. That's a number not equal to -1. So power rule with n equal to -1/2. What do we get? Well, we get 1 over -1/2 plus 1 x to the -1/2 plus 1. What's -1/2 plus 1? Well, if you have $1 and spend 50 cents, you're left with 50 cents. So 1 minus a half is a half. We have that 3-tiered fraction. 3-tiered fractions are unsimplified. Multiply by the reciprocal of 2 over 1. 1 times 2 over 1 is 2. So we have our 2x half using the power rule. Power rule works for all exponents other than -1. Any questions about part B? This one really does have a lot to it. How about part C, tangent x cosine? Well, first of all, we can't do an integral of a product piece by piece. There's no antiderivative rule, there's no integral for products. Well, there's no general integral for products. But what can we do? Well, maybe this simplifies a little. Sometimes these do simplify a little. Sometimes, not all the time, but sometimes, we can simplify this by turning things into sines and cosines. Maybe that'll help us. Maybe it won't. Doesn't. Tangent x, sine over cosine. Cosine carries along. And look at that, cosines cancel. Maybe that simplification will work. Does it? Well, do we know a function whose derivative is cosine of x? Yes, we do. The derivative of sine of x is cosine of x. Oh wait, that's not what we want. Maybe I should have turned my back. Do we know a function whose derivative is sine of x? I think I was thinking cosines because we canceled them. Do we know a function whose derivative is sine of x? Well, the derivative of cosine is negative sine. Derivative of cosine is negative sine. So right here, this doesn't work because the derivative of cosine is negative sine. But with our third property, or not our third property, our second property, part B, negatives can carry through integrals. Negatives also carry through derivatives. Or you could have just said from property 6 in our list, derivative of negative cosine x is positive sine x. Either way you want to see it. When doing sines and cosines, I mentioned this in some homework feedback for problem, or some exam feedback for problem 8. With sines and cosines, we sometimes have negatives, we sometimes have positives. And they're sometimes difficult to keep organized. What I like to do is always keep in my mind the derivative of sine is cosine and use that to make sure my negatives are right. Derivative of sine is cosine, so the derivative of cosine is negative sine. Negatives cancel, and this works. Any questions about that one? Okay, now sometimes turning things into sines and cosines works. Sometimes it doesn't necessarily work that nicely. I'm just looking at the worksheet to see what we have. Well, for the homework, you don't really have to turn sines into cosines or anything like that. You know, there could be one like problem 4D where, you know, you have like a tangent or something in the way, and it turns into a secant tangent, something like that. But sometimes turning things into sines and cosines work. Any questions about either of these, any of these three computations? Okay, let's do one more type of indefinite integral computation, and then we will do definite integrals. This next type of computation is called an initial value problem. It's right here. It's terrible, man. INITIAL. Initial value problems. Well, recall the definite or the indefinite integral gives a family of functions. Different by a constant, but the indefinite integral gives a family of functions. So now that C can be any constant, so it gives a family of functions. But what would need to happen for us to get only one of those functions? Well, if we threw a condition on what this F must satisfy, what this capital F must satisfy, then we could solve for a specific constant. So, and we're going to call that condition that this capital F must satisfy, we're going to call that an initial condition. How do I want to write this? But, does that be on screen? Yeah. But an initial condition will allow us to solve for a specific C value, for a specific C, capital C. C value. What is this going to look like? Well, there are two general ways this could look. What did I write in the it's not the notes, the homework and the other thing, worksheet. Yeah, so on the homework, on homework number 3 is going to look like this first example. Worksheet number 5 looks like this, but done, twice. So let's do a couple of these. Let's do 2 of these. Solve the initial value problems. Maybe I should say solve each initial value problem. Part A. Well, now let's write it first. Antiderivatives go backwards from derivatives, meaning start with a function, take a derivative, you found the derivative. Start with a function, take an antiderivative, you've gone back a step. Meaning, if you start with a derivative, you can go backwards to an original function using an antiderivative. This notation says what all antiderivatives look like, but we could interpret this process using a derivative and going back to a function y in terms of x. So we can start with a dy dx and go back to a y equals something with x. So here we have dy dx. Here's the derivative. Here's a condition on y. Y of 0 is 3. Let's do one more. That's not where I wrote it. Well, we didn't do this. Let's list one more and then do both. B. We can interpret our derivative as a rate of change. Rate of change of position is velocity. So let's say we're given a velocity function. Velocity equals negative sine of t. And let's give the velocity is the derivative of condition. So we can, of position. So an antiderivative of velocity would give us a position function. Denoted with an s. And let's say s of 0 also equals 3. Okay, both of these are 0 equals 3. So let's do both of these. What notation do I want to use? Okay, that's a good notation. So in each case, that second part is our initial condition, our condition on our antiderivative. So part A, since dy dx equals x squared plus 2, we can find y by taking, well, we can find a general form for y by taking the indefinite integral. And then we can use that condition, y of 0 equals 3, to find a specific value for y. So what do we get here? Well, we have a power rule, we have that first constant rule, the third x cubed plus 2x plus constant c. Take the derivative of this right-hand side, you get x squared plus 2. So that is a correct indefinite integral. But we can solve for a specific y, a specific function y, meaning we can find a specific c value using this condition. Y of 0 equals 3, but y of 0 equals 3. What does that mean? Well, when x equals 0, y equals 3. So when x equals 0, y equals 3. So we get on the left side 3 equals, what happens on the right side when you let x equal 0? 0 plus 0 plus c. We need a specific c value. We have here c equals 3. So that tells us what? Well, it tells us what our y function is that satisfies the initial condition I erased. So y equals the third x cubed plus 2x, and we found that c value of 3. We found that c value of 3 satisfied that initial condition. Any questions about part A? And we can also check our work here. Derivative of y with respect to x is x squared plus 2. And also, it satisfies the initial condition when x equals 0, y equals 3. So right there we had for an x and y function, y in terms of x. But here we have another application for part B, where we have a position function, and we're trying to find a position function given a velocity function and a condition on position. So let's do this same thing. I'm going to erase this because it's always good to try to not look at previous work when trying to solve new work. Helps you learn what you don't know. So let's try this one. Actually, I'm going to give you a minute or so to try this one because I'm running out of comfortable chalk to use. So try this one for the next minute or so while I go down the hall to get more chalk. Taking a little more than a minute. Lots of good chalk. So what do we have here for part B? We have a velocity function. Let's find a position function which satisfies these two equations. The derivative of position is velocity. So going backwards would give us a general position function. Well, maybe I'll say position function, which I always want to call P, but standard to call S. The position function is integral negative sine of t. This time we're integrating with respect to t because that's our variable. And what does this equal? Well, the derivative of sine is cosine. So the derivative of cosine is negative sine. So again, with sines and cosines, I always like to go here. Write an answer and check that the negative signs work. I find that much easier than remembering the list of rules. Does this work? Well, the derivative of cosine is negative sine. So yes, that works. The negative signs are all in their proper places. Any questions about finding a general position function? That was my dropping my keys, in case there was a noise. So we need a specific position function that satisfies s of 0 equals 3. So you may be tempted, in the first question we had s or y of 0 equal 3, c equals 3. But c here does not equal 3. I think it's going to equal 2. Let's check. But s of 0 equals 3. So what do we have? When t equals 0, position equals 3. So 3, what happens when t equals 0? Well, we get cosine of 0 plus c. What's cosine of 0? Cosine of 0 is 1. Why is cosine of 0 1? Well, you could either memorize it, you could either do it 500 times until it becomes memorized, or you can go to the unit circle. Angle 0 over there, 0 units around the circle. We're going to carry 1, 0. Cosine is the x value, so cosine 0 is 1. So that gives us c equals 2 in this case. So the general position function we want is cosine of t plus 2. Any questions about either of those initial? Well, any questions about the second initial value problem? Any questions about either initial value problem? Okay. So we're going to come back to these indefinite integral computations tomorrow, but for now we have another integral to consider, the definite integral. Debating how I want to start the definite integral. Let's do it like this. You may not want to write this sentence as I'm writing, because I might go back and change a word or two. I'll tell you when it's the way I want it to be. So the first, 80 minutes of today, we discussed indefinite integrals, and we discussed their properties, we discussed some rules for them, and we solved some initial value problems. Definite integrals today are going to look much different. Is that the camera case? Sorry, it's kind of hard for me to tell exactly where the board ends because my erasings go about 5 inches to the right of that, to the left of that. Definite integrals. Recall, fortunately for these definite integrals, we've actually done a good amount with them already back in week 2. Okay, so recall, back in week 2, we discussed area between a curve and an axis. We assumed that the curve was above the x-axis. We'll generalize that today. But recall, that exact area A, so the area between a function and a piece of the x-axis, we discussed how to approximate that area. We also discussed how to find that area exactly, that exact area. And we said, well, our approximation was with rectangles, with n rectangles, but we said if we let the number of rectangles go to infinity, the approximation became exact. And we had 2 approximations, and in the limit, each approximation gave that exact area. We in week 2 did not actually cover this exact area computation. We might do that today, we might do it tomorrow, depending on time. I'm not overly concerned with it right now, but I will become more concerned with it after a couple of results tomorrow. So there's our first recollection. LN and RN were the left and right hand approximations, sometimes called Riemann approximations, left hand, right hand. Riemann, R-I-E-M-A-N-N, after mathematician Riemann. So there's our first recollection. We assumed that this area, well, we assumed that this function was above the x-axis for computational convenience when first introducing them. But what would happen if this were below the x-axis? Well, if it were below the x-axis, there could be 2 different interpretations. And we're going to discuss a little about them right now. Let's say it like this. What about, what if f of x went below the x axis? What would that look like, and what would this approximation do when we made it exact by taking the limit? Meaning, what if we had, I don't know, something like this. Here's our function. A and B, yeah, I guess I'll use A and B again. There's a function, goes below the x-axis somewhere, and here's our function. What if that happened? What would that area approximation do? Here, we recall how we did our approximation. What did we do for our approximation? We divided an area into rectangles. We said the height of the rectangle was given by the function evaluated at x for each x between a and b, for each x that we picked between a and b. So what would we get up here? I'll write a third graph, do I? I'm going to draw 2 graphs actually here. Well, actually, sorry, I'm going to just change this first graph. Sorry about that. I should have built up to that. Sorry about that. That's not enough area. Okay, third try, fourth try will work. Okay. So here's our function. Here's A. Here's B. There's the area in consideration. What would happen if we did the same exact approximation we did in week 2? What would we get? Well, we'd have a left or a right. Let's just pick one of them for now. Let's pick a different color. Let's do red or something. No, I did left, so maybe I should do blue. If you did that same exact approximation of that area, what would you get? Well, you'd still get some rectangles, but notice the height of the rectangle, or the base of the rectangle is given by a piece of the x-axis. The height of the rectangle is given by the function evaluated at x. We always took the function evaluated at x. So in this case, when the function it was below the x-axis, what would happen with our approximation? Here, the rectangles with area, what was the area of our rectangles? Well, it was given by the function evaluated at x times some change in x. You know, sometimes you see this change in x written b minus a over n or something, but you could just write it as a change in x. The x-axis piece times the function. The rectangles have that area with our interpretation of that approximation. The rectangles have that area, but notice f of x is negative. So in our approximation that we did, these rectangles below the x-axis are going to contribute negatively. Notice I'm not saying the areas of the rectangles are negative. I'm saying with the approximation we did, remaining consistent with the approximation we did. Each rectangle piece with height f of x is negative, so this is becoming a negative, or this piece of our approximation would have been negative for each of these rectangles below the x-axis. So again, they're not negative areas, but as far as our approximation is concerned, it thinks of these pieces below the x-axis as negatives. Any questions about that? And that's a little subtle. We will, next week, we will see an interpretation. Now for this week, for our interpretations, we are going to think of these as negatives. We will see an interpretation next week where thinking of these as positives tells us what we want. But that's next week. But with this in mind, let's define the definite integral and discuss what it does. Definition. Let f of x be continuous on a to b. The definite integral so first we discussed indefinite integrals, here definite integrals. The definite integral of f of x denoted integral f of x with respect to x looks a lot like the indefinite integral notation, but we're restricting ourselves up to the interval a to b in our notation that will show up at the top and the bottom of our integral sign. B on top, A on bottom, let's write it smaller so it looks less squished. The definite integral of f of x denoted, I guess I didn't write this smaller, but I did write it less squished. That's a terrible one. The definite integral of f of x with this notation, just like the indefinite integral, but there's an a on the bottom and a b on top because we're looking at the interval a to b. If it's not continuous, you could split it up more on that. Let f be continuous, definite integral with that notation, comma, is defined as what? Well, let's define it and then discuss it. A little more on this area after we define it. is defined a to b f of x with respect to x equals the limit as n goes to infinity of the left-hand approximation, and it also equals the limit as n goes to infinity of the right-hand approximation. So right here, definition of the indefinite the definite integral is the exact area from our approximation. Sometimes in computer science, you see, I assume it's Java, I don't know computer science languages, but colon equals means equals by definition. So here I am going to use that just since there are two equal signs here. Definite integral equals by definition. So colon equals this limit, and that limit equals that limit by previous discussion from week 2. So we have this. Let's consolidate this definition and those area observations from before in a remark. And in this remark, I'm going to want to start it over on this side. So right now, definite integral gives us the area that we found using our approximations. That approximation, if we're being precise, counts below the x-axis negatively, counts above positively. Remark. Let f be continuous. Yeah. More on what happens when it's not continuous when we do a couple properties. Let f of x be continuous on a to b. If it's not continuous, you can split it into its continuous pieces and just do it piece by piece. Let A1 be the area between f of x. I'm going to have a graph over there illustrating this. And the x-axis that lies above the x-axis let A1 be the area between f of x. Sorry. I should put this here. I was going to put a clarifying thing at the end, but it should be in the middle. Let f of x, or let A be the area between f of x and the x-axis. Interval. Let A1 be the area between f of x and the x-axis. Even in my notes, I don't like how this sentence is written. This is going to be written better. Let A1 be the area between f of x and the x-axis interval a to b that lies above the x-axis. Here. Let A2 be the area between f of x and the x-axis interval a to b that lies below the x-axis. I'm just going to say lots of periods below. So A1 area above the x-axis, interval a to b. A2, the same exact thing, but below. So you could write the same sentence twice from, but just changing A1 to A2 and above to below. But what happens in that case? Then what? what does the integral of f of x on a to b, definite integral, what does that equal? Well, do I want to give it away, or do I want to do a drawing first? Let's do a drawing. So this will say equals something and something else, which will be the end of the sentence. But let's draw what we have. Now we can use a curve like the one I had over there. Here's f of x. There's a. Let's say there's b. Here there's only one piece above the x-axis. There's one piece below. A1 is the total area between f of x and the x-axis on the interval a to b that lies above. A2 is the same but below. What does the integral give us? Well, remember, the integral by definition gives us the exact area that we got from our approximation by letting the number of rectangles go to infinity. What does that approximation do for areas above? Well, the rectangles have positive heights. F is positive, causing the approximation to view these as positive. But below the x-axis, the rectangle would have what can be considered a negative height as far as that approximation is concerned. And as far as that approximation is concerned, these pieces below the x-axis contribute negatively to the area. So the definite integral treats what's above the x-axis as positive and treats what's below the x-axis as negative. Any questions about that? So it is useful in the back of your mind to have this approximation and what we did for the approximation. It's useful to have that in mind. And as far as the definite integral is concerned, it may be useful to summarize that in your mind as above the x-axis is considered positively, below is considered negatively, as far as the integral is concerned. But there are going to be times where it's useful to view that as a positive, and we're going to just define that here. And total area between f of x and the x-axis interval a to b is treating it all as positive areas. So any questions about this? This is a little theoretic, but it all goes back to our approximation of the area. And with what we were doing, what was below the x-axis would be thrown out as a negative. And the integral measures that. So any questions about that? I think it was a remark. Okay, let's do two examples. Example. Consider following with areas given. So here we have a function. Let's throw an arrow. Let's mark off some areas. Let's mark off some x values. -1. 1. Not too many ones. 4. Now I want it to be odd. -1. 3. 5. 7. So here we have a function. Let's fill in these areas now. I didn't give you areas yet. This first area, let's say, is 2. That's a number. So that whole area is 2. This next area, it's a function. This next area, let's call 3. I know I'm using 3 twice, but that'll be okay. And this last area, let's say, is 4. So right here, these areas are given. First piece above the x-axis is area 2. Next piece below the x-axis from 3 to 5 is area 3. Last piece from 5 to 7 has area 4 and is above the x-axis. So here's what we're given. And let's find some integrals. Evaluate. Let's evaluate 4 things. Integral from -1 to 3 f of x. Part B, integral from 3 to 5 f of x. Part C, evaluate integral from -1 to 7 of f of x. Part D, total area between f of x and the x-axis interval, I'll just say and the x-axis interval -1 to 7. I'll abbreviate that like that. So -1 to 7. It's an x-axis interval. I don't put it right like that, but that's fine. So let's evaluate these. So remember, these first 3, we have some definite integrals. They're definite because there are numbers at the top and bottom. And what does the definite integral say? Well, it says I see areas above the x-axis as positive, and I see areas below the x-axis as negative. First, part A. We're just looking at, in part A, from -1 to 3. So we're looking only from -1 to 3. What happens to this function from -1 to 3? Well, there's a piece above the x-axis with area 2. It's above the x-axis. The integral considers that positive. Any questions about part A? Okay, now part B says the integral from 3 to 5. What happens from 3 to 5? Well, from 3 to 5, well, we're looking from x value 3 to x value 5. So we're looking between 3 and 5. What does the function do there? Well, there's this piece with area 3. And this piece with area 3 is below the x-axis. So this integral is not 3 because it's below the x-axis. The definite integral treats areas below the x-axis as negatives, making that a -3. Any questions about part B? Okay, how about part C? Well, part C says look from -1 to 7. -1 to 7, that's everything we have. So from beginning to end. What's above the x-axis is considered positive. What's below is considered negative. What's above the x-axis is a 2, area 2, and an area 4. What's below the x-axis is negative. There's just a -3 there. So what's above is positive, below is negative. 6 minus 3 is 3. That's not a -3, that's an erasing. That didn't go away. Any questions about part C? Okay, what about part D? Well, part D doesn't ask an integral, it says what is the total area? The total area sees every area as positive. So 2 plus 4 plus 3, they're all positive as far as total area computation is concerned. 2 plus 3 plus 4 is 9. Any questions about part D? Well, any of these parts really? Okay, let's do one more like this. So in this example, I gave you the areas. Let's do one where I don't give you the areas. Well, if I don't give you the areas, then they better be convenient shapes. And they will be. They'll all be, circles, trapezoids, rectangles, triangles. Trapezoids, of course, are rectangles and triangles attached. Example. Let's do the function, and then let's find what we want to find. I should draw that a little bigger. Okay, here's a function. Throw an x-axis, a y-axis somewhere. Let's make this -4, -3. Let's make that 4. Let's make that 5. Let's make that 6. Let's make that 9. Let's call this f. There's f of x. Notice this is a continuous function. More on that in a moment. Evaluate. A, integral from 5 to 9. Yeah, 5 to 9. B, evaluate integral from -4 to 9. Let's make these numbers look less bad. 5. So evaluate this, these integrals. Now, you could see circles. I believe on the worksheet I threw a circle on there. Circle has area pi times the radius squared. Oh no, it wasn't the worksheet, it was the homework. Circle has area pi times the radius squared. I will tell you on the homework for problem 2A and problem 2C, you need that semicircle that I labeled semicircle. The radius is findable from that, even though the y value isn't given. The y value is findable. But how would we do this? Well, you could jump straight to the integral. With these, I tend to like to fill in the areas first and then just throw numbers where they belong. So right here, it looks like we have a couple trapezoids, but area of a trapezoid formula is pretty complicated. But instead, I'm just going to turn this into triangles and rectangles. Now with those lines, it's not a function anymore. But those lines serve to, oh, I didn't give all the y, geez. Give your y values there, 2 and -3 I wrote. Sorry about that, you need these y values. Pretty hard to do without those y values. Sorry, 2, -3. And we can find areas of right triangles, we can find areas of rectangles. The rectangles are the one side times the other. So this rectangle, the one side is 7, the other side is 2, making a 14. This rectangle, the one side is 3, the other side is 3, making it a 9, so it's actually a square. And now we have these right triangles. What's the area of a right triangle? Well, it's half times the base times the height. But for a right triangle, the base and the height are given by the legs. So the area of this first triangle, it's a right triangle, the base is 1, The height is 2. Half of 1 times 2 is 1. Is that right? Half 1 times 2 is 1. Yes. For this next triangle between 4 and 5, the base is 1. The height is 2 again. Half of 1 times 2 is 1. For this next triangle from 5 to 6, base is 1 again. There's the base. The height this time is 3. Half of 3 times 1 is 3 halves. Now, when you fill in these areas, and you could interpret the negative in a couple different ways. You can interpret this as a negative for your purposes, and the other one below the x-axis as a negative. I tend to leave the areas as positive and interpret the negatives when we need to using the integral. But either way you want to do it is fine with me. But what do we have here? 5 to 9, integral from 5 to 9. Start at 5, go to 9. What's above the x-axis is positive. What's below the x-axis is negative. There's a 3 halves below the x-axis. There's a 9 below the x-axis. So we have negative 3 halves, minus 9, negative 3 halves, minus 18 halves, negative 21 halves. And again, if you wanted to write the areas in the diagram as negatives when they're below the x-axis, that's certainly okay with me. As long as you interpret them correctly over here, but however you want to see them. Any questions about part A? Okay, what about part B? Well, part B says we're looking everywhere from negative 4 to 9. What's above the x-axis is positive. 1, there's a 14, there's a 1. What's below the x-axis is negative. There's a 3 halves below the x-axis, there's a 9. So what do we get here? 16 minus 9 is 7. 7 minus 3 halves. 14 minus 3 is 11, so 11 halves. Any questions about that? Okay, well, that'll be all we do for right now. Tomorrow, we will, well, I'll mention a couple properties of the definite integral. I'll mention a little more what happens when it's not continuous. If it's not continuous, you can imagine this rectangle going way up here. The interpretation would be the same. But we covered today the definite integral and the indefinite integral. And the indefinite integral gives a family of antiderivatives. The definite integral gives an area. The indefinite and definite integrals have very similar language and notation, even though the one gives a family of antiderivatives and the other gives an area. Why do they have such similar notation and language? Well, we will cover that tomorrow in the fundamental theorem of calculus. Fundamental theorem of calculus will relate lots of what we did, including it'll say this area computation and this family of antiderivatives are actually very nicely related. So we'll do that tomorrow.